Hello, everyone. Welcome on the workshop teaser for the Mastering C++ Stud Execution framework. It's also called senders receivers because this is how it was originated. But officially, it landed up in C++ 26 as a Stud Execution framework. But you don't have to wait for C++ 26 for this actually to be used because it is working on C++ 20 language. And there is a reference implementation from NVIDIA and other companies as well that you can actually use right away. And actually, plenty of companies are using this in production already as we are speaking about this workshop here. All right. So this is just a preview, right? A teaser, 45 minutes. So I will try my best to actually teach you something meaningful. But if you want to actually learn a lot about this Stud execution, you should attend the full training after the conference. And basically, then you will learn a lot about senders receivers, and you will be familiar and will feel comfortable in using that at production, at work after that. But first, let me introduce myself. My name is Mateusz Pusz. We can call me Matt. I'm so-called modern C++ evangelist by my friends. What it means is that I love sharing my experience and knowledge about C++ with people. If you ask me on corridor any questions about C++, after half an hour, you will be sorry that you asked because I will be talking and talking and talking. I will not shut up. So this is me, right? There are no stupid questions, and I promise I don't bite. So please ask me questions. I will be really happy to answer them. I'm doing this for more than 20 years for fun and living, right? I am the author of the MP units. Maybe you've heard about it. This is my fun part. And also I worked at Intel for 15 years and EPAM systems for 10. So this is my living part where I actually deal with production code. I did many different positions in many different companies through the years. And also I'm a trainer with 15 years of experience. So I'm doing this quite long for right now. I'm coach, mentor, consultant for many corporations, and a conference speaker. Besides that, I'm also active voting member and contributor to the ICC+ committee and to some other working groups in the committee as well. I'm also a member of Mistra C++, and my main interests are code performance, low latency, safety, and maintainability of the code. My training motto is to master C++ with your fingertips, not just your eyes, right? I just provided another teaser in a second, so you can find it online and on YouTube. But already we had a lot of discussions, lots of code, and actually there's also a hands-on exercise that you can do during the teaser, and during workshops we are going to do them for sure, right? There will be plenty of exercises, plenty of hands-on, because this is how you learn to write code, right? Looking at slides doesn't teach you how to write code. My experience is that when I show some code to my students, they understand the code. They can say exactly what the code does, or even what is the problem with the code. But then when I ask my students to write something 3 times simpler, they don't know how to start. Okay? This is where actually this muscle memory comes in, right? You have to actually do active practice to make the knowledge truly stick, right? You build muscle memory and attend workshops, write code by yourself. That's why all of my workshops are hands-on, first with plenty of discussions and plenty of writing code by yourself, right? Of course, not every training is equal. Some trainings are a bit more about theory and discussion. Some trainings are more about coding, but there's always plenty of hands-on exercises on my workshops because I really think this is really important, right? And yes, those are not easy. Those are not like simple hello world exercises. You will sweat a bit, but this is in a really good intent to make your knowledge last. Typically, during the exercises when you're doing online sessions, we use Zoom breakout rooms where we basically split the students into 3 to 5 person groups per room, and they work together on an IDE, which typically is just a compiler explorer link. They share the screen with others, give the control, and work on a solution in a group, which allows us to progress quite fast. We switch roles. And I always encourage people to be active, discuss, and share feedback with others, because you also want to learn from each other then. There's also a button called Ask for Help, when you can actually request me to come to your room and provide you immediate feedback or help you when you are stuck. When you're done, just leave the room and go basically to the main session and wait for everyone to finish. After the class, I'm going to provide, after the training, actually provide two workshops. One workshop is concurrency in the standard library. We had another teaser about it a few minutes ago, so you can find it online. And other workshops will be about structured concurrency with senders and receivers. So basically state execution. Those two are just a part of my modern C++ concurrent asynchronous programming workshop that I provide for corporations in 4 days. You can check the full training offer here, but let's scope on what will be provided at the conference. So with the state execution training, you will get all the information about the motivation, framework introduction, sender receivers algorithm library, error handling, performance optimization, structure spawning, state execution versus coroutines. I hope that you know a bit about coroutines. If not, those will be still simple exercises, so you can actually reason about them, because state execution is created with the compatibility and interoperability with coroutines in mind. And also I provide some hints how to test asynchronous code. Unfortunately, due to time constraints, this is just 1 day session. We are not going to cover this one chapter with custom senders and schedulers, because it's like 2 or 3 hours of talking how you can write your custom blocks by yourself. But if you have any questions about it, just let me know, and I will show you some examples as well, if needed. So this is the part of entire training that we are going to cover after the conference. But today we are on a teaser. During teaser, I will try to briefly introduce you the framework, and this will work a bit differently than the previous teaser, because this time I cannot assume you know anything about that. So I will not ask you questions. There will be no discussions at this point, because, well, you don't know what happens because this is new. Previously, we basically were basing on something that you should already know at least a bit. So this is a bit different, but anyway, we are doing lots of exercises later on. All right, during 45 minutes, it's really hard, but I will at least try to provide you introduction. So maybe this session will be less interactive than typically, because we are not having enough knowledge to actually start doing real work. In 8-hour training, you will going to do a lot of work. And why we need to do this work? Because basically right now there's no software that is not asynchronous or parallel, right? The Herbstarter provided a nice talk a long time ago called "Free Lunch is Over," right? We are not getting CPU frequencies going up for free all the time. We have to start to dealing with the clocks we have, and in order to make our applications faster, we have to actually start working on multiple cores rather than on one core only. So because of this, we are going into concurrency, parallelism, and asynchronous programming world, where it applies to all of the software right now, right? And affects every engineer that is basically associated with C++ or any other programming language actually in today's world. So this is crucial really knowledge of how to deal with that. So let's talk about structured concurrency. Or maybe first, let's talk about actually GoTo programming. Lots of applications can be written only in terms of GoTo, right? Actually, plenty of all of the programs written in 60s or 70s were written in terms of GoTo, right? All of those punch cards and other stuff, they were written exactly with GoTo programming. But we don't do it anymore, right? Why? There are no scopes. It's too easy to create infinite loops. We have problems with lifetime. We have hard to understand control flow. It's nearly not possible to reuse. Right? You can write a code with GoTo still today, right? But that is so-called spaghetti code. And by the way, I cheated here, right? I use functions, I use for loop because it didn't fit on my slide. So it's not pure GoTo like in 60s. But this works. This is some sorting algorithm. Do you know why it's called spaghetti code? At this point, when this code was written, like in 60s, 70s, we even didn't have monitors, right? Everything was printed on a paper or written by hand on a paper, right? And then you've had all of those things on a piece of paper, and what you are going to do, every time you see GoTo, you are making a line to where it goes to, and then another GoTo where making a line of when it goes to. And there are so many GoTos and so many lines that the code starts to look like this mess. That's why the spaghetti code term was coined. Okay. Edgar Dijkstra in 68 already said that GoTo statement is considered harmful. Brian Cunningham and Dennis Ritchie in 78 So the fathers of C basically said goto is infinitely abusable. So we know for a long time that goto is wrong. As a solution, we created structural programming. We introduced branches, control flow, scopes, while and for loops, and so on. Functions called subroutines at this point, right? This structured our programs from goto. So new language mechanics replace equivalent flows which previously would have been written using gotos and ifs. And why I'm talking about this? Because structured programming versus concurrency is exactly the same, right? Computation are for concurrency, what functions are for structured programming. As of today, we have plenty of those gotos in the standard library or in the OS. Mutexes, all of those logs, semaphores, right? Threads, all of those low-level facilities that do not provide any structure to your code. You have plenty of possible problems like data erasers, deadlocks, and so on, because there's no structure forced by the design. You are living in goto world with the current abstraction that we are going to talk about on the workshop, actually, after the training as well, after the conference as well, right? But you have to know those low-level primitives often to actually deal with our commercial software. But on top of that, you can use structured programming. And structured programming provides you whatever is built on top of gotos for regular functions, right? Fire and forget task models are unstructured, right? We can have some compute async operation that has some local data and executes some async function, passing reference to this data. All right. I will not ask what's wrong with this code because we already discussed this on the previous teaser. Basically, it is going to go out of scope, right? It never rejoins. It's detached work, and it can go out of scope, and you may refer some data that is not there. And there's nothing that prevents you from that, right? Both threads progress independently. There's manual resource management. You cannot use unique pointers here. You cannot use any other array object because you typically pass stuff to callbacks or whatever, and then lifetime is gone, all right? I mean, like automated lifetime through array. And you have to manually synchronize because you never know what is being accessed from where, right? We shared memory to all of the cores at the same time, to all of the threads at the same time, right? Everyone sees everything in the RAM, at least, right? So everything can be shared, everything can be potential problem. It will be much better if the actual language was created this way, that nothing is being shared, and you have to specify exact pipes of communication between different threads to say this thing is used for sharing, this thing is used for sharing, so then you can provide some proper guarding around those primitives. But no, everything is going to shared. Everything is possible to be referenced from multiple threads. Everything is potentially dangerous, and if you're not using structure to your programs, you have to deal with this manually, and this is what happens typically in production, and typically this is what crashes in production at some point. That's why bringing structure to asynchrony, bringing structure to concurrency is really important. Right? So we have plenty of concurrency primitives and low-level building blocks, but we lack standard vocabulary and frameworks for asynchrony and parallelism that C++ programmers need to write efficient code. Async future promise are inefficient, hard to use correctly, lack generality, and this makes them unusable in many contexts. Parallel programming was a good start, but they are synchronous and not composable. Future is inherently inefficient and cannot be used to efficient composition of asynchronous operation. We have allocation deallocations, we have atomic increments decrements, we have synchronization between stating of the result and getting the result. If you're using .then extensions, which are non-standard, this provides some scheduling overhead, and also it's hard to reason about this work because when you actually start the future, this work may already have started already. It's already working, so it's hard to already prove that there are no races. Right? A future is a handled work that has already been scheduled for execution, which may be a potential issue. Structured concurrency is about making abstractions as building blocks to provide recursive decomposition, local reasoning. We will have only single entry and single exit point, And we want to have the design that is really to reason about by inspection, right? So design forces you to write correct code. Coroutines are structured concurrency, right? A waiting coroutine has single entry and single exit point. It composes nicely. You have scopes, you have array AI, you have lifetimes. In coroutines, everything works nicely. It's so much better than callbacks. It removes a lot of burden from the programmer and improves performance because of it. So please use coroutines. We're not going to talk much about coroutines on any of these workshops on this conference. I will provide some workshops before on other conferences, or we can talk about this on a full 4-day training if you would like to hire me as a trainer. However, there are some problems with coroutines. Coroutines do not natively support cancellation, right? In many cases, at least for tasks, for asynchronous tasks, a dynamic allocation may be needed to actually make the coroutine state. It might not be an issue, and typically I don't want to say it's an issue because typically it's not. When you're dealing with asynchronous I/O, typically you have other bottlenecks in your software, right? In your program. If you're dealing with asynchronous I/O for networking or for file I/O or whatever, then the cost of one allocation is not that big. And coroutines are really easy to work with. So I don't want to say that coroutines are bad. They are awesome, and you should learn them for sure. They are much better than anything else that we had before. If you want to learn more about the allocation engine, you can find this paper called Halo, and you will find out more when the allocation may be elided for coroutines. What about callbacks? Callbacks are actually the simplest, the most powerful, and the most efficient mechanism for creating chains of work. However, they can propagate either errors or values, and there is no standard shape of them. So multiple vendors provide different callback structures, and they are basically inherently uncomposable. And also, there's no nesting of scopes and lifetimes. Array doesn't work, so it's not a solution as well. The goals for the executor's proposal, so the proposal actually before the send receivers, but the goals are the same, was to have an asynchronous analog of the standard library algorithm. So we're going to talk about algorithms in those training. We know about algorithms, and we are talking about algorithms as of today. We think about data algorithms, right? All of those find, if, sort, and so on. Right now, we're going to talk about asynchronous algorithms, and those will be totally different. Those will be things like when and then and when all and so on, right? So different algorithms, and we are going to have to deal with this. That we will have different algorithms in the standard library after that. This is an open and accessible way to specify where, how, and when the work should happen. And encapsulates algorithms like then, when all, sync, wait, repeat, when any, timeout, and so on. A standard set of abstractions, concepts derived from algorithms. They will be composable and generic. They should be easy to be corrected by construction. It should be efficient to work with coroutines. Errors must be propagated, but should not be a burden for the user. And they should support cancellation, which coroutines do not support. All right. Cancellation is not an error. It's just a work that is no longer needed. For the training and for production, you can actually use std.exec library from NVIDIA. This is a reference implementation of official standard paper accepted for C+26. It is C+20 implementation, so you can use it right away, assuming you have C+20. It's header only, and there are different headers and different namespaces in this library. Basically, what is in a std.exec directory or namespace std.exec, those are the things that are already proposed and accepted for standardization. Exec are some extensions that are not in the standard. NVExec are, of course, for NVIDIA hardware, and ASIO-exec are useful if you want to deal with Boost ASIO. But during the training, we are going to deal with those. And how this framework looks like. We have a scheduler. Scheduler is a handled compute resource. Schedulers work on an execution context. Execution context may be heavy. Scheduler is meant to be lightweight, right? It's like a std allocator being basically handled to actual allocator, right? So this is similar. Sender is a unit of lazy work. async work typically, right? It describes the asynchronous operation, can be chained with other senders to create pipelines, and sender is a factory for receivers and operation states. So what is a receiver? Receiver is a basically completion handler, a callback that can accept values or propagate values, errors, and cancellation. And operation state is your basically non-movable persistent storage for entire lifetime of the asynchronous operation. It's similar to coroutine state, coroutine frame, if you are know what coroutines are, right? Coroutine frame basically is being used to steal data, and we are putting data from promise types and awaiters there to actually make this data persist for entire operation. So in this world, this is operation state. This is how it looks. Scheduler has a schedule function that returns you a sender. That is typically an input for the pipeline. Sender will have a connect function that connects with receiver, and when you connect the sender with receivers, you get the operation state. You can also query some environment, but we are not going to talk about this right now. And receiver has those three channels for values, for errors, and for stops cancellation signals. If you connect sender and receiver, you will get an operation state. Operation state just have a function start that starts the asynchronous operation. As a user, you just deal with blue boxes. You have schedulers and senders. This is what a user sees. All right, nothing else. You don't deal with receivers and operation state. You even don't know that they are there. You just have schedulers and senders, and this is what you are dealing with. But actual work is being done by receivers and operation state, and this is done under the hood. So if you're going to be an algorithm implementer, then you have to know about it. Otherwise, this is not that important, but still it's good to actually know that they are there and what they are responsible for. So what is different between scheduler and execution context? An execution context is a resource that represents the place where execution will happen. A scheduler is, as I said, a lightweight handle to this execution resource, right? It is a strategy for scheduling work onto an execution context. Schedule function returns a sender that will complete on execution context determined by this scheduler. For example, I may have static thread pool of 8 threads. I call get scheduler. This is non-standard, right? Exec. I call get scheduler, and I already get something that satisfies the standard concept, right? This is concept. This is constraint on the left-hand side of auto. This is concept name. I put those concept names so you know what I'm dealing with, because just using autos everywhere will be hard maybe to reason about. And typically you want to use autos here because spelling this type is impossible. It's like trying to spell a view. If you play with views already, you know that you don't want to write view type explicitly. This is similar. This is onion-like architecture. It will just nest and grow, nest and grow, nest and grow to some monster. You don't want to write it. You're just using auto, and with concept, you can say exactly what it is, what's category of it, so it's easier to reason about the code. Then if you have the scheduler, you may say schedule on the scheduler, and you will get a sender that's the begin of your pipeline. Senders help separating the logic of an algorithm, the work you actually care about, from details of where and how they get executed. Senders allow writing the program logic once and then decide how to execute it without changing the program logic. You can execute it on a single thread, thread pool, GPU, or another execution context. So for example, I can write begin, just result text. I provide some file name to the pipeline. And then I'm saying this is the previous block, then gets this previous block and calls this functor. So this basically this result text goes as an input to this functor and does some operation on the file. Right, so this is similar to views. You can pass the previous element in the pipeline as the first argument of the next element of the pipeline. And of course, you can also pipe them. I'm going to show this in a moment, right? Unlike C++70 parallel algorithms, senders allow chaining multiple asynchronous computations, which is much better than the algorithms that we have, without unnecessary synchronization. With senders, user can describe generic execution pipelines and graphs, and then run them on across variety of different schedulers, right? Notice that I didn't specify where it's being run at all. I just specified what's the work I want to do. And I can put it on anything, single thread, thread pool, GPU, and this work will just be executed there. I can specify just 42, pass 42 here, get 84, then pass it here, and then get another 42 increment. Similarly to views, senders support chaining with pipe operator or operator, right? So you can write this code or this code. Those are equivalent, they are doing the same. I typically prefer this code, so this is what will be showing you on slides mostly, but also from time to time I will provide you this code, so you are basically getting familiar with this as well. And we have different kinds of senders in the library. We have sender algorithms, and those are basically sender factories. Algorithms that take no sender and return a sender. Sender adapters that take senders and return a sender. And sender consumers that take senders and do not return a sender. So this is the beginning of the pipeline, the middle of the pipeline, and the end of the pipeline. Sender factories and adapters are never allowed to submit any work for execution prior to returned operation state being started later on. Well, with maybe some exceptions that we're going to mention during the training. And they're also guaranteed to not start any input blocks passed into them. Sender consumers such as std exec sync wait start the operation state. So sender consumer, right? It takes some work and it will synchronously waits for the result. Because at some point you need to get a result from the asynchronous calculation. So at some point you need to block to actually wait for the asynchronous operation to finish. And this is what is doing that. It just blocks your current thread and you're waiting for data. Sync wait will return you optional of tuple of values sent by the last sender. This is why I'm calling here value, because I want to get rid of this optional part, and then I'm left with the tuple part. That's why I'm using structure bindings to unpack the results to specific bindings here. Even if last sender returns you only one value, this will still be a tuple of one element. That's why you're going to deal with the structure binding a lot with this framework. Sync wait will return you empty optional in case a cancellation happened. That's why optional is there actually. Or sync wait will throw an exception if there was an error in the pipeline. So it's similar to future get that also throws an exception if there was an exception being in a thread or a task. So now we can summarize and see the entire pipeline. The simplest pipeline will be to have a scheduler, so basically a factory, then move it to an adapter that will transform it in some way, and then put it to the consumer that will wait for will start the work and wait for the work to happen. And you can write the same with pipes. Right? You have scheduler, then, and you're waiting for this to happen. Those pipelines may connect in any different possible ways. This is so-called onion architecture. So basically, it wraps receiver, the receiver, operation state, and you call start. And when you start it, it may finish with set value, set stop, or set error, and then the algorithm may basically propagate any of those inputs to any output. Depending on the logic of the program, you may have, or the logic of the algorithm that you are actually executing with, it will be working in a specific way, right? Like for example, then block will just propagate the errors, will propagate this cancellation with no modification to the next block because then doesn't deal with those explicitly. And set value will either end up as a value here or as an error in case a lambda in then throws an exception. Right? But there are totally different also blocks like upon error. For example, upon error will take an error and put the error to the value channel. All right, so every possible connection is possible depending on the logic you want to implement in a block. Notice that also every adapter has a chance to run code when the operation is starting and when the operation is finishing. Right? So adapter will be like this one. This is operation state for the adapter, and this is receiver for the adapter. We can do some operation before starting the next block, and then we can do some operation when we get actual input from the previous block. Okay. All right. And now the simplest exercise we can do that is not too trivial, transferring the work. Right? We have some schedulers, and with schedulers, you may say I'm scheduling this operation to happen on sketch 1, and then you want to continue the rest of the pipeline on sketch 2, and you are done. Right? It may be CPU, it may be GPU, it may be NVIDIA, it may be AMD, it may be anything, and it just works. And this is what you're writing as a user. You don't care about anything else. The data is being propagated for you, it's being synchronized for you. You don't have to reason about what happens under the hood. Those don't have to be different hardware. Those may be the same CPU, for example, but you may have something like IO pool and work pool, and then just propagate between those pools. And you don't have to do any explicit synchronization here because everything is handled for you by the framework. Right? So framework by itself will never transition from execution resource to another execution resource by itself. You have to be explicit about it with the blocks like continuous on or schedule. You can query the completion scheduler with get completion scheduler for specific signal. And in this case, I have CPU scheduler, GPU scheduler. I start on CPU, then I write them on CPU. I continue on GPU, then I write on GPU. And I can ask get completion scheduler for the value channel on the environment of sender, and I will get something that's equivalent to the CPU scheduler. And when I do it on sender 3, I will get something that's equivalent to GPU scheduler because the pipeline is aware in this case where it has to be executed because it was encoded in the pipeline. It doesn't have to be, but in this case, it was encoded in the pipeline. All right. So an exercise would be to actually play with this transferring of work a bit, right? So basically writing a simple pipeline by yourself with the blocks that you already know. And this can provide you some examples with them already. And trying to call legacy read from socket on the IO pool. And then leave the IO pool because you want IO to be to not spend too much time on processing the data because you want to wait for another packet to happen. And put the work on that long working task here for legacy process data on the work pool, on one of the threads from the work pool. All right, so you have IO scheduler, work scheduler, two different pools. You have some socket. This is just a stub here for the Compile Explorer, right? And you have some buffer for data. And you want to implement this work in your exercise to make it work and actually start reading this legacy reads from socket on the IO pool, then continue the work on the work pool, and then do legacy process data on the work pool. All right. Actually, I don't have a chat here, and this bothers me a bit. I just have a Q&A, which doesn't help. So I cannot share you with the link to this exercise easily. But anyway, we have just 10 minutes to the end of this of this teaser. So it will be pretty hard for you probably to finish. So maybe as an alternative, I will do this live. Typically, I don't do live anything on the workshops. You are working by yourself, but as it might be hard for actually to pass you the link right now, maybe I will just do live coding and maybe we'll see how it works in practice. But please try to do it by yourself at home, all right? Because this is meant for you to make it to basically to teach your fingers how to type it. Oh, I think I provided you the incorrect link here for the other training. Sorry, how it happened? All right, the link is incorrect. I will have to fix it on my slides. Oh, no, let's try again. Okay, I didn't update the link properly. I have the link here. Okay, I have the link here, and For people online, I will update my slide in a sec, and will show you the slide with the proper link. For some reason, I just copy-pasted the link from another teaser that I just did before. Sorry for that. Just give me a moment. All right, let's build it. And let's present you with proper link to the exercise. All right. So now the link is correct, and you will be able to, through this link, you'll be able to get to the proper exercise and then try it out at home. All right. But let's try to do it right now together, because I said we are short on time, so we are not able probably to do it in 3 or 5 minutes if you are never actually worked with this framework. So what we want to write here, first we want to schedule this work. Right? If you want to schedule this work, you're writing something like stud exec, and it looks easy to type by yourself, but you will find out that it's not that easy as it seems, because you have muscle memory already. Typically what people type, and also it often happens to me that I typing it this way, because stud : is basically stronger than me. I cannot just write something besides colon after std. It's really hard to actually type it if you are not used to that. All right, then we want to put the work stud exec with then block. All right, and we want to have something like that. Return legacy read from socket. And you want to pass the socket, buffer data, and buffer size. So all of the arguments required by this call. All right. And then you want to continue on work scheduler. Notice that it's called continuous on, not continue on, right? Continuous. So it's important to learn it. And then you have something like that. Size t, read len, because we need to pass. We get the size from it, right? Because legacy reads from socket returns you the size t, returns you the count of data that was read. Right? So you get this. You get the value here from this function. It goes here as an input, and then you have to basically use this to call legacy process data. When you pass the buffer data again, and read len. And it should work at some point. What did I do? Should exec work. Schedule, not scheduler. A size, or I have a size. Typo. You will notice that the compile times here are far from being nice, right? Because this is quite template-heavy machinery. And also you'll find out that errors are not that nice. If you ever deal with coroutines, in coroutines, compiler messages are beautiful, are great, because coroutines is language-based feature. Synthesis receivers is pure library feature, so the compiler doesn't know about it much, and the errors are much worse, right? So you will struggle with the errors, but during the workshop, we are going to play with those errors, and you'll get more familiar and comfortable with them during our exercises. But it's basically what you do and how you make those exercises work. This is the simplest way of making it work. You could make it even more advanced here, and I will show you the solutions to make it even more advanced, because right now the buffer is just referenced outside with the reference lambdas, which may be a potential issue if you don't want to wait in the same function, because otherwise those may go out of scope. So typically you would like to actually put this data into the pipeline itself. And during the workshop, I will show you how you do it and how to make it work, so you're having actually the data in the pipeline, so then you can return work from the function, all of those go out of scope, and you are still fine. But for now, actually that's it, and we don't have much time to actually finish anything more, because we are nearly out of time. So if you like such an experience, if you would like to get more familiarity and more experience with this framework, hands-on experience, because looking into the slides, listening to the talks will not teach you that, I promise you. You have to train it, you have to try to type it, you have to fail, and only if you will fail a few times, you will learn. This is how people learn, and you basically have to accept that, right? So come to the workshops and learn it, right? And this is true for everyone, right? For everyone and for every workshop, not only mine. So attend also other trainers' workshops if you so desire, right? But workshops and lectures are totally two different experiences, right? Here you are learning by doing, not just by seeing, which is totally different thing. And also, if you like my strategy, if you like my basically my approach to the trainings, and you would like to get more, please consider hiring me as a trainer. I provide this 4-day training on entire concurrent asynchronous programming with all of the concurrency in the standard library, coroutines, and senders receivers in 4 days. This is a great modern training about concurrency. I also provide a really great training about the language itself. It's probably the most popular trainings I provide. It looks easy, but it's not. Promise me, it's not. You're going to sweat, but you're going to learn a lot, and you're going to understand how language works, and this will make you much better programmer. And I have some design trainings as well. C+20 trainings and CMake Colon trainings, but you can find my full offer at my website. And that's basically it. We are out of time.